Hello, everyone. Welcome to this webinar on getting started with AWS App Mesh, which is a part of MI2 webinar series, which stands for Machine Intelligence on Modern Infrastructure. My name is Janakiram. I'm based out of Hyderabad, India, and I'm excited to bring you this series of webinars covering AI and cloud native technologies. So the machine intelligence revolves around artificial intelligence and IoT, while modern infrastructure is all about Kubernetes and containers. And today's session, I'm going to walk you through something which is still emerging, which is called as the service mesh. And for the reference architecture, I'm going to take help of recently announced service from Amazon, which is AWS App Mesh. But before we get started, I want to launch a quick poll to get a sense of how you actually use service mesh or how many of you are familiar with service mesh. Interesting. So it looks like most of you are planning to use the service mesh rather than using it already, which is completely expected because this is such a new technology and it is evolving rapidly. So I expect service mesh to become mainstream in the months to come. So coming to today's agenda, I'm going to give you a brief overview of microservices because service mesh is appreciated in the context of microservices, and it makes a lot of sense to do a quick recap of what are microservices and what it really means to embrace them. And then we'll take a closer look at the challenges involved in adopting microservices and see how service mesh addresses some of those challenges. And then I'm going to introduce you to AWS App Mesh, particularly in the context of a service mesh, and walk you through a detailed demo where we'll actually do a canary rollout of microservices running on Amazon's EKS controlled through AWS App Mesh. So let's get started. Now, if you are very new to microservices, this background might help you understand and appreciate how they are going to be helpful in deploying modern applications. So 90s was all about three-tier architecture, which is now, of course, legacy and traditional. But when it got started, it was a very powerful way of developing applications because there was a clean separation between data, middle tier, which was hosting the business logic, and the UI component that was predominantly running inside the browser or a thick client deployed on the desktop. Even today, most of the enterprises still follow this application architecture. J2EE, .NET, and most of the traditional enterprise applications use this architecture and design for running their applications. The challenge with this approach is when you are actually scaling out, you're going to create a cluster of application servers. And this application server cluster could be running a J2E app server like WebLogic or WebSphere, or it could be running .NET or Complex or one of the distributed computing platforms that essentially run the entire stack on each application server. Now, the components that are actually called as C1, C2, and C3 are deployed inside the application server. They could be enterprise Java beans, or there could be complex components or CLR services. It doesn't matter. They are logical units of deployment that are running on every application server. Now, when you are running this architecture, what happens when the load is so high that the application servers are not able to access or not able to serve the expected response? So you need to add another application server to the cluster, maybe AS5, and that is going to again run C1, C2, and C3. But carefully analyzing the current context and current deployment, you'll notice that maybe C1 is the component that is getting the maximum load, while C2 and C3 are lying idle. But the problem with this approach, which is actually called as the monolith, is that when we launch a new application server, you also need to launch C2 and C3. There is no way that you can maximize on C1 while reducing the footprint of C2 and C3, because the way an application server is designed and the way these components are designed to run within the application server, we can only replicate an application server at one time. So essentially the deployment unit is an application server running either on a physical bare metal server or in a virtual machine. And this doesn't really solve the problem, and there is no resource utilization that is optimized. Now, imagine moving to an architecture that is slightly more horizontal, as in we run multiple nodes, and then there is a cluster manager, and the cluster manager is basically orchestrating and managing the entire distributed environment. And the logical unit of deployment has come down from a large server to a component. So now, because we are looking at an aggregate pool of resources coming from node 1, node 2, and rest of the other nodes, we can actually launch more number of components. For example, in this scenario, you'll notice that there are C3s running more than C1 and C2. That's because C3 could be the component or the service that requires better scale, and that could be the bottleneck. And eventually, when the requests start coming to more of C2 and when it needs to scale out, the cluster manager can automatically reduce the footprint of C3 and increase the number of C2s. So this is very, very advantageous because ultimately what this results in is better utilization of your resources and better utilization of your hardware and CPU, memory, and storage. So this is a very modern way and efficient way of running software. And each of those deployment units are now called as microservices. And the infrastructure on which it runs is now either Kubernetes or a slightly modern platform like a Mesosphere or DCOS. So ultimately, the idea is to pool multiple resources and run deployment units at the service level rather than at the VM level. And each of these services are obviously packaged as containers that are managed by the cluster manager, which could be Kubernetes. And data is also going to be actually split. Again, for simplicity, I left the data part as is, but data could be decentralized. So instead of having one large Oracle or SQL server, we might actually have a MongoDB, a Redis, and other cloud native database that is actually supporting each of those deployment units. So data is also highly decentralized. And of course, UI is changing. We have a variety of clients that actually deliver the user experience. So everything is different, but I'm basically zooming into the middle tier and the application server and showing you how this basically delivers better scale. So we are moving away from looking at VM as the unit of deployment to a service, and a service could be packaged as a container. So every service, which are depicted here as S1, S2, and S3, are completely independent. They are autonomous. They are designed as if that is the only service running in the entire application. But when you assemble these services together, they all deliver a unified application experience. So this is very high level. This is like a crash course on microservices. So here you basically take a function, which is, and by function, I don't mean serverless or function as a service. By function, what I mean is a business function that is supposed to perform one task at a time. And you wrap that as a microservice, and you deploy it as a Docker container, and you can scale in and scale out depending on how this service is going to respond and how it is going to be behaving at the deployment and runtime. So this is microservices architecture at a high level. But as you notice, these microservices are actually written in a variety of languages because the services are highly autonomous, fine-grained, and independent. It is possible to handpick best of the breed languages, tools, and frameworks to write each of the service. For example, if I'm doing machine learning based analytics, my service would be written in Python. If I'm actually doing some kind of model view architecture, and I'm actually using an MVC kind of a thing, I might actually choose Ruby for one of my services. And if I'm doing some legacy interop and legacy integration, I might choose Java as one of my languages for the microservice. It really doesn't matter what language you're using, because microservices always expose a unified communication pattern. For example, all of them would expose a REST endpoint, or all of them would expose a gRPC endpoint, or any other lightweight communication protocol. So as long as it has a well-defined entry point, it does one thing at a time and has a graceful exit and is autonomous, it qualifies to be a microservice. So you're actually going to handpick best of the breed languages, tools, and frameworks. And the challenge with this is, eventually when you want to do something that is more centralized, for example, I want to actually now do two things. One, I want to figure out how long it takes for service A to call service B, and how long it takes for service B to call service D. So I have to really intercept the traffic that goes out of service A into service B and rest of the chain of services. Similarly, my service C, which is written in C# is calling an external service, and I might actually want to figure out the communication pattern there, and I want to measure how long it takes for me to call an external service and have better control over my inbound and outbound communication. It is fairly easy if you're actually using one language to write this kind of an interceptor or an agent that is going to be attached to each of these services, and it is responsible for figuring out how the traffic is flowing in and out. But the problem is you cannot really standardize or generalize that, because you're actually using a variety of languages. And if you end up writing those agents, you got to write it in the language in which the microservice is written, which means to basically monitor and control service A, you got to write an agent in Python. And for service B, you got to repeat the same functionality, but in Java and in C# and in Ruby and so on. So these agents, some call them SDKs, some call them agents, some call them frameworks. It doesn't really matter, but the job of an agent is to closely monitor the functionality of this service and also monitor the communication pattern of this service. It might also report into a centralized environment, right? For example, there could be a centralized monitoring service to which all these agents are reporting to. And that central service could be responsible for communicating with the agents and getting the telemetry data. For example, what is the health of service A? What did it just do? Which service did it call? And how long it took? All of the telemetry might be sent to a central service, but we'll touch upon that a little later. So for an organization, writing agents for each of these languages that are deployed in every microservice is going to be very expensive, because they have to maintain the source code and the IP, and they have to repeat this functionality every time they implement a new service in a new language. That's not all. Each service actually uses a different protocol. For example, you might use protocols to talk to the microservices via HTTP, HTTP2, gRPC, GraphQL, sometimes PubSub mechanism based on Redis, or even MQTT if you are using some kind of an IoT. So you have a variety of protocols that are actually used for communication, and the agent needs to understand all these protocols, because what happens if your service is now exposed using GraphQL and the agent doesn't understand what it really means to communicate via GraphQL? So it has to be aware of that protocol. So the agent is not only written in different set of languages, but it also needs to understand a variety of protocols. And this is another challenge. It's not easy. And on top of that, you might actually scale out your services. For example, if you're using Kubernetes, you might want to create a replica set or a deployment and run multiple instances of service B, and you might want to load balance. So you'll actually put an L7 load balancer, depending on the type of service that you're exposing. If it is using low-level sockets, then you might actually want to use an L7 load balancer. That is basically, I'm actually sorry, L7 is based at the highest level. It's the application-specific HTTP protocol. So you're actually using it as an internal load balancer for L7, and you're load balancing the traffic across multiple services that are running an agent each. And then to expose service A to the outside world, maybe you're using an L4 load balancer. So your agent need to understand the nitty-gritties of the OSI model, and it needs to intercept the traffic that is flowing across multiple layers of the networking stack. And that's not easy again. So, and again, when you have these polyglot agents running with diverse set of protocols, diverse set of load balancers, they all need to ultimately roll up into a central monitoring service. Otherwise, there is no point of having an agent. So these agents intercept the inbound and outbound traffic. They monitor the health of every service, and they constantly send that telemetry data to a central monitoring service. And this central monitoring service could be another microservice, or it could be a VM-based deployment. It doesn't matter. But you need to create that central monitoring service and ensure higher availability of that. So effectively, an organization is investing in an infrastructure that is going to be very fragile, very brittle, and is bound to change with every new service that is going to be deployed, and very hard to maintain, because they have to really own this entire platform. And this platform is becoming very, very essential for microservices, because when you run microservices, there is absolutely no visibility into how many services are running, what is the health of each service, how do they communicate, how long is it actually taking to communicate, and what happens if one of the services is dead. So to track all of this, you need to implement this infrastructure. There is no going away from that. But the question is, should you do it, or can you borrow this whole concept of an agent plus central monitoring service that intercepts communication, telemetry, and does everything that we discussed? It is possible, but before we get there, let me summarize the challenges that we discussed so far. First of all, microservices is all about polyglot programming. You choose best of the breed software, languages, frameworks, tools, and technologies. So every developer is different, and they are actually using language specific tools and SDKs. For example, a Java developer might want to use a different toolkit to basically manage his microservice, and they talk different protocols like HTTP to GraphQL to gRPC to sockets to whatnot. And there are multiple deployment targets. This service could be running inside a physical bare metal machine. It could be running inside a VM, or it could be a container, or it could be a Java Jetty server wrapped as a jar file. We never know where it is going to ultimately end up running. That's another challenge. And it has to deal with a combination of load balancers, both internal and external, L4 and L7, and a variety of network protocols and communication techniques. And it also becomes very complex to debug once the software is deployed in a microservices pattern, because you cannot really trace the whole call chain and figure out which microservice is rogue or acting strangely, and how it is basically slowing down the entire application. So debugging is another big challenge. And of course, it all stems from the fact that there is no visibility and observability at the microservices level. Centrally monitoring and observing your entire deployment is not easy. And increasingly, it is becoming hard to implement the best practices of distributed computing. Now, there are multiple techniques. For example, there is circuit breaking, there are retries, there are a variety of techniques that you are expected to implement when you are adopting a distributed computing pattern. Now, unfortunately, with microservices, it is increasingly becoming hard to implement any of that. And finally, security is a big problem. Decentralized authentication and authorization, because the same challenges apply to security as well. How do these microservices inherit identity, and how do we define very fine-grained role-based access policies for each of those services. So all these are the challenges that we have touched upon. So that leads us to the service mesh. So what is a service mesh? Well, a service mesh is a very consistent layer of software that is going to deliver on the concepts that we discussed so far, which is like an agent that is going to attach itself to every microservice, and it is going to report into a centralized control plane. It does health checks, it does real-time monitoring, it does logging, tracing, and it implements best practice of distributed computing. All of this without an organization investing in agents and a centralized control plane to manage those agents. All of this comes out of the box. And the best thing is this can be out of process to existing microservices, which means this service mesh that we are talking about pretty much follows the same pattern, but instead of writing the agent in a specific language and making it in process, we are now talking about creating an agent that pretty much runs with any microservice written using any language, running any protocol, without really making it very tightly coupled or tightly bound to the microservice itself. It's a highly detached out of the process component, or a sidecar, or a proxy, or an agent, whatever you call. It attaches itself to the microservice, and it talks to the centralized control plane. It supports internal and external load balancers, a variety of load balancing techniques. It does service discovery. For example, you can figure out what are the services available in your deployment and how to consistently talk to them, what are the well-known endpoints. All of that is delivered by the service mesh. Has extensible protocol support, from gRPC to even talking to MongoDB via your service mesh becomes very easy, and it can understand and proxy through it. It does advanced health checks. It will basically monitor the health of each service and can report any issues with the health of any service, and provides a lot of insights and delivers great observability into your distributed computing deployment based on microservices. So service mesh is essentially what an organization would want to develop, but it is something which is available out of the box, and they can start deploying it irrespective of the languages, protocols, load balancers, and any other polyglot diverse environment they may have. So how does this work? Well, a service mesh has two components. The first component is the control plane. The control plane is like the command and control center for all the service mesh agents that are running or attaching itself to the services. And these agents are officially called as proxies because they are literally proxying a service when it is talking to another service, and they intercept the traffic for both inbound and outbound, and they literally take over the communication, pretty much like how a proxy server takes care of your outbound and inbound traffic. The proxy that is attached to the service takes care of the entire communication mechanism. And because it is in a mesh topology, it's logically called as a service mesh. And this proxy is also called as a sidecar because it is an out of process component that is attached to every running service. And all these proxies are managed by the centralized control plane, the command center. And the command center constantly talks to the proxy, and it pushes any policies, any rules, and any specific routing policies that you may want to implement. At the same time, every proxy reports the health of the microservice and its current state back to the control plane. So it acts as a remote control to any number of proxies that are deployed as a part of your microservices deployment. And these proxies are language agnostic, protocol agnostic, microservice agnostic, and network agnostic. They can pretty much attach themselves to any microservice that is running as a part of your deployment. Now, there are multiple implementations of service mesh, and AWS App Mesh is one of the most recent entrant into the service mesh world. It is based on a very popular open source proxy called Envoy, and Envoy came from Lyft, where Lyft basically struggled with the same set of challenges that we spoke about, and they implemented Envoy as their proxy that attached itself to every microservice, and it is a very robust, mature proxy for microservices. What AWS has done is it has taken an Envoy and built its own control plane, which is a managed service. Like RDS, for example, has a control plane that you don't get to deal with. You'll only talk to it via the CLI or the portal or the SDK. But the control plane orchestrates your RDS deployments and manages the health of your RDS cluster. Similarly, App Mesh has a control plane through which you're going to communicate with the overall proxy deployments and the current proxies. So the data plane is running an Envoy proxy, and AWS has also attached a router, which is like an Istio mixer, to the sidecar, and a combination of Envoy proxy and the router are deployed with every microservice, and they talk to the managed control plane, which is actually monitored, managed, and made highly available by AWS. And App Mesh precisely does two things. Number one, it is going to control the communication and traffic flowing in and out of microservices. So think of the communication pattern of App Mesh as a combination of a load balancer plus a firewall. So whatever you do with the combination of these two, you can pretty much do that with the App Mesh proxy, that is, or the Envoy proxy and the router combination deployed as a sidecar. From now onwards, I'm going to call it as a sidecar. So the sidecar is a combination of the load balancer plus a firewall, because what you do with a firewall, you can pretty much achieve that with the sidecar, because you define inbound and outbound rules, the ingress and the egress rules, and you'll also enable load balancing, because this proxy is responsible for routing traffic to a lot of internal services. So it's a good mechanism, or a good analogy to think of it as a combination of firewall plus security group, or firewall plus load balancer. That is the first job of App Mesh. The second job is the telemetry that is streamed from every microservice to CloudWatch, or even third-party monitoring services like Datadog. So you will get a lot of observability data coming straight from the data plane of App Mesh to CloudWatch, or a third-party service like Datadog. So bottom line, an App Mesh deployment will result in better control of your microservices communication pattern, and then it delivers a lot of insight through monitoring and observability. So those are the two promises delivered by App Mesh. Not just App Mesh, any service mesh is responsible for these two tasks. So mapping the concept that we have discussed so far with App Mesh, as I mentioned, there's a control plane that is invisible, directly managed by AWS. It's highly available and is responsible for accepting the policies and maps and service discovery information via the CLI or the SDK. And this control plane talks to every proxy. The yellow dotted line that you see is the communication between the control plane and proxy. So it is like a client server, though it's not very appropriate. It's like a client server. The server is a control plane and the client is proxy, and they have a constant dialogue on the current state of the deployment. So there are certain concepts that I want to introduce, but before that I want to show you a slide. So this slide actually makes it easy to visualize. So the control plane has three components: observability, which is monitoring; network management, which is the combination of load balancing plus firewall; service discovery, which is making microservice 1 discover microservice 2 and enable intra-service communication. And to this control plane, we basically send our definitions as maps, and these maps directly match your deployments running in Amazon EKS or ECS or Fargate and eventually EC2. And also the policy definition on how the traffic can be routed, what is allowed, what is not allowed, and what are the available ports. So basically all those definitions will be sent to the control plane, and control plane will take that maps and policy definitions and applies them to the proxies running as sidecars to every microservice. So that was the big picture. Now coming back to the key concepts of App Mesh. So a service mesh is essentially a logical boundary for network traffic between a variety of services. For example, if you have deployed 4 services and all the 4 services will talk to each other in a mesh topology, then you define a mesh, which is going to be the logical boundary for all the 4 services talking to each other. And it becomes like a dotted line within which the services will reside. Then every service is mapped to what is called as a virtual node. It's a logical pointer to, for example, an EKS deployment. Now, in Kubernetes, a deployment typically translates to a set of pods exposed and visible through a service endpoint. So you create a deployment and then you create a cluster IP, and the combination of this deployment plus cluster IP is what is represented as a virtual node within service mesh. But this nomenclature and jargon is independent of EKS, ECS, Fargate, and EC2. This is a logical service deployment or a representation that is basically mapping to one of your actual deployments running in your compute environments like EKS. And then every virtual node has a router attached to it. So the job of a router is to basically make sure that the node is able to accept the traffic, and it is basically advertising the node to the rest of the services. So it basically implements the DNS equivalent for the virtual node, and it announces itself to the rest of the world saying, hey, I'm the router representing this node and I accept traffic. So that is the job of a router. So a router is attached to the node, and to the router, there are multiple routes. So a route is basically the inbound traffic, right? For example, how exactly the traffic is going to be routed and which virtual node will receive, and what are the rules that will define the outbound traffic. All of that goes into the route, and the route is attached to the router, and router is attached to the node. So think of virtual router as the container for a variety of route definitions. So if you want to define a route for a virtual node, you need to have a router, and that is the association between this. By the way, virtual node is independent of this. You can create a virtual node without a router, without a route. It can still exist, but it will not have any policies associated with it. So it pretty much relies on its calling components to talk to it. It doesn't have any policies directly attached to it. And at the same time, a virtual router can route the traffic to multiple virtual nodes. So it is actually a mesh because you can create a variety of topologies with the concept of virtual node plus router plus route. More of that later. So this is how you define a virtual node. A virtual node essentially has 3 elements. So I put excuse me. So I put the graphical representation and the actual JSON definition. So every virtual node will have a backend. It has a listener and it has service discovery information. So the listener will define the ingress, what is the inbound port. For example, here we have a virtual node that represents an order component, and this order service or component listens on port 5000, accepts traffic originating from or using HTTP, and it can talk to product and customer as backends, and it advertises itself as the endpoint that is put here. And by the way, this is the official DNS name that can be resolved within and outside of App Mesh. It is a proper DNS endpoint through which the service can be resolved or can be accessed. So that is the actual definition that goes into the service discovery. So that's how you will define virtual node. So if you carefully notice, this is a straight mapping to a deployment plus cluster IP in Kubernetes, because it has the definition of the compute, which is the node itself, and then it has the service discovery information followed by the inbound traffic and outbound traffic. So this is the virtual router. As I said, virtual router is a container for multiple routes. Um, at a minimum, a virtual router will only have the service name defined for the virtual node. It is meant for service discovery and self-advertisement to let other nodes know that it exists. And to this virtual router, we attach multiple routes. For example, in this screenshot that you see here, we have a virtual route called order R, and it is associated with virtual router called order VR, and it has a target for 100% going to the same virtual node, which is order VN, and it is used via HTTP. And it matches a condition where prefix is root. We are simplifying it here, but basically the combination of this virtual route definition, the router, and the node effectively represents one logical entity, which is called the order. And this order belongs to a mesh called shop mesh. And eventually, when I define my other virtual nodes called product and customer, they also belong to the same mesh. So that's how we end up creating multiple virtual nodes, multiple virtual routers, and then multiple routes. And this is how they all come together, and this is how we connect the dots. So as I explained earlier, that is how we basically define the policy and send these policies to all the running proxies via the control plane. So now it's time for us to build a real world application. And I'm pretty excited to show you this. I put a lot of effort to simplify this concept through live deployment. So what are we actually building? Well, there are 3 microservices that we're going to deploy. One is called as an order, which is the gateway service, which means it is accessible publicly on the public internet. And then there are internal services called product and customer that are invoked by order. And each service is a Kubernetes deployment with an associated service. Order is a load balancer type service, whereas product and customer are type cluster IP. Now, we'll first deploy V1, and then after we go live with V1, while the application is still running with 0 downtime, we will deploy V2 of product service and drive 50% of traffic to V2. And once that stabilizes, we'll deploy V1.5 of customer service and drive 25% of the traffic to customer version 1.5. And as we observe the overall feedback from the system, we will increase the traffic, and eventually we'll drive 100% of traffic to product V2 and customer V1.5, and then terminate the instances and delete the virtual node and associated routes from the first version. And all of this on the fly with no downtime and impacting the live deployment. So let's go ahead and do this. And to visualize this, this is how it's going to look like. So order is exposed via an ELB, and then order talks to product V1 and product V2. The dotted line represent like a blue-green deployment or a canary deployment. And we are going to eventually retire V1 and only use V2 or V1.5. So that is the demo. So let's get started. And by the way, I want to announce that this entire script, source code, and everything that I'm going to show you is already available on GitHub. You can clone this repo and you can start exploring this tutorial. Tomorrow by this time, we'll also have a step-by-step guide published at the New Stack, who is our media partner. And you can wait till tomorrow to see that article go live and use those steps to basically set up your entire environment and follow through the steps to repeat the whole tutorial in your own environment. So, okay, this is not building and deploying machine learning models. This is about building and deploying App Mesh with Kubernetes. So let me get started. All right. So I have a split window here. Let me show you the demo structure. So I have 3 folders here. You'll actually see services, and this services contains the source code for each of the microservices that we have built called order, product, and customer. Now, these services are already built and pushed to Docker Hub. So I'm not going to spend a lot of time on that. Then we have this folder called mesh, where you can create the mesh for each of the versions. For example, by default, if you don't mention any version, it goes ahead and creates the mesh and all the virtual node and router combinations for V1. So once we do that, we come to Kubernetes and then deploy V1. And once this is deployed, we'll basically test the entire deployment. And once it stabilizes, we will come back to mesh, and then we will update the mesh for V1.5 and V2.0 and roll out the Kubernetes equivalents, and then define a policy that's going to do the canary release for us. So let's get started. Now, how does the environment look like? Well, I have EKS already configured. So I have a single node EKS cluster. So I want to keep this very simple. The idea is not to overwhelm you with a lot of services and a lot of complex jargon, but just a single node EKS cluster running in US West 2. And we are going to start by deploying the actual the actual application. So it all starts by the creation of the mesh. And how does this mesh look like? So let me show you the definition of our mesh. So this is the shop mesh. First, we'll create the shop mesh with order node, and then we will create the virtual routers, virtual routes. Basically, we are going to do it for V1. So first, we will do it for order. Then we'll do it for product. For example, this is the product virtual node. So this is the product virtual node. And then we'll do it for the customer virtual node. And then we will associate the routes and the router. So basically, I have automated all of this through a script. There are multiple commands that we need to run. So instead of actually running one command after the other, I have simplified. If you really want to see what it takes to create, this is the script. Basically, we first create the mesh called shop mesh. Then we define the entities representing order virtual node, virtual router, and the routes. We repeat the same for the product and customer. So by end of this script, we actually have a fully configured app mesh. And remember, at this point, we don't have the Kubernetes deployment. This is purely a logical representation of the deployment. So this is just like a placeholder. Eventually, these placeholders will be populated by the actual DNS names that are lighting up when we do the Kubernetes deployment. So for now, let's go ahead and create the mesh. So let me move to this folder called mesh. And we run this command called create mesh. So this is going to basically first create the shop mesh, and then it will create all the entities that we discussed so far. And this will set up the mesh infrastructure for running V1 of Kubernetes. While this is going on, I have the actual client, which is running inside a container. I'm going to launch that. So this pod that we have is going to help us access the services. So let me keep this running. So the app mesh deployment is done. And now I'm going to move into the Kubernetes deployment. And I'm going to execute a script that says deploy V1. So now we are going to deploy v1.sh. And what this does is, it's pretty simple. It is taking kubectl and deploys the V1 of all the deployments and service endpoints. So when we actually do a deploy V1, it's going to create three things. It's going to create a product deployment exposed by a product service endpoint. It creates a customer deployment and a customer service. And I already cached order because ELB will take a long time. So it basically created all these three. So now let's take a look at the number of pods we have. So when I do a kubectl get pods, forget about the curler, it is the client. But you'll notice that there is the customer pod, order pod, and product. So when we do kubectl get service, we'll actually see associated services. For example, there is a customer service as cluster IP, product as cluster IP, but order is a load balancer, and it is available on this public C name of the load balancer. Now, instead of accessing through this load balancer, I'm actually using the curl command. Let's check out what the customer service will send when we access. So when I actually do a curl, it does nothing, but it basically sends the metadata saying it's a customer service and version is 1. I can pretty much do the same thing for the product, and it is going to show us the service name is product and version is 1. Nothing fancy here. It is basically a placeholder which is sending the metadata. Then we can actually do curl on the order, and order is slightly interesting because what it does is it actually shows, oops. Okay, I'm unable to access my order service. Let's see if, okay, no problem. I'll access it through the public IP address. Okay, so what I'm actually going to do is I'm going to remove my deployments and do it again. Remember, this is a live demo, and live demos are slightly risky, but they're also exciting. So I'm going to do a live demo, but I am going to remove all the deploys. So I'm going to get rid of all the deployments, and I'm going to do it afresh. Give me a second, bear with me while I reset my demo. Looks like there is some problem with my previous deployment. That's where we had this. So now I'm actually going ahead and deploying my V1 all over again. And what it means is it's going to create the ELB. That's fine. It's going to take a couple of minutes. While that is happening, I will try to access my services again. So kubectl get pods. I should have 4 pods running. Perfect. Kubectl get service. I should have 4 services. There we go. ELB is still under pending, which is okay. Now let's go ahead and do a curl on each of our endpoints to make sure we get the desired expected output. So first I'm going to check customer. The service is not there yet. Maybe let me check. Okay, now it is on. I didn't include curl there. It's in. Okay. All right. So now I'm actually checking the product, and now it's time for me to check order and see if this really works. There we go. So now we notice that when we actually do a get request on the order endpoint, we notice 3 versions, 3 different versions of the services. So basically order is invoking customer and product. So we get to see the version from each of these services. Perfect. So now we have V1 running, and what we'll do is we are going to kick off a constant loop where we will get the current version of all the 3 services. So currently order is in 1.0, customer is 1.0, product is 1.0. Now the goal is deploy customer V1.5 and drive only 25% traffic to it, and then launch product V2 and drive 50% traffic to it. So let's do that. So we will now move to the mesh directory again. And what I'm going to do here is basically define a new virtual node. And this virtual node, okay, let's actually look at the virtual node for the customer. So okay, I'll show you the definition of a customer virtual node that belongs to V1.5. So customer V1.5, and this is the virtual node definition. So this is the actual virtual node that is reflecting the V1.5 of customer virtual node. And it actually has a Kubernetes DNS endpoint, which is resolving to its own endpoint. So this is a standalone entity. Our order at this point doesn't even know that we're actually deploying customer V1.5. Everything remains the same, but thanks to App Mesh magic, when we deploy 1.5 and when we actually define a rule, which looks something like this, this is going to basically drive 50% of traffic to V1.5 and 50% of traffic to v1.1. And customer vn, it's like the latest, so I didn't prefix it with the version. So by default, customer vn represents v1, and customer v15 or v15 vn represents version 1.5. And now we added a rule to the routing policy, that belongs to customer virtual router. So whenever there is traffic coming to this route, split 50% and send it to v1, and split other 50% and send it to v1.5. So that's what it really means. Now we are going to do an update mesh to v1.5, and what it does is it basically takes the latest JSON definition. Remember, the control plane accepts the routing policies and the rules, so we submit the latest policy to the control plane. We come back to Kubernetes and we go ahead and deploy 1.5, and this reflects customer version 1.5. So this is going to now, what it basically does is it takes the customer deployment, creates a service, and it results in a new set of pods and services. So now you have customer v1.5 as a pod, and there is also a new service associated with this pod, which is basically this, and it's again a cluster IP. But nothing is showing up here because we haven't really done the canary release. So now I come back to mesh and I do a deploy canary for v1.5. And what this does is it takes the latest JSON definition that we put here, where we are saying drive 50% of the traffic to v1.5, and immediately rolls it out. So when I actually hit enter, in just a few seconds, we should notice that the customer version will now oscillate between 1.0 and 1.5. It will take just a few seconds, but very soon we should be able to, there we go. So now 50% of traffic is routed to version 1.5 of customer. And the beauty is this, we haven't brought down the deployment. We haven't done anything with the live production deployment. We just rolled out one tiny component of the whole application, which is the customer microservice alone. And we are able to route 50% of the traffic just to this microservice. This is beautiful. Doing this with VMs, it's such a pain. Now, let's repeat the magic for product version 2.0. So what I need to do is first update my mesh for v2. So this is going to create the infrastructure for onboarding v2. Once that is in place, I come to Kubernetes and I basically deploy v2 of my application, which has an update to product. And once this is in place, I do a canary release. So deploy canary for v2. Now see the magic. Now it's going to route traffic to product v2. And what rule does it really define? Well, let's take a look at it. So here we have product canary. And again, product canary is also routing 50% of the traffic to v1, which is the default, and 50% of the traffic to v2. And there we go. Now, I had an immense satisfaction when I looked at this demo the first time, because this is brilliant. This is how microservices are expected to work, and we are implementing the best practices of distributed computing. Order is still version 1.0, and it is randomly calling, not randomly, based on a well-defined policy, calling version 1.5 of customer and 2.0 of product in a very selective fashion. Now, what is missing in this demo is the telemetry. If I am observing the telemetry, it will give me a lot of insight and also confidence whether I should really roll out 100% of this. But for now, I actually take that call, and looks like everything is working perfectly well. So what I want to do now is to route 100% of traffic to customer 1.5 and 100% of traffic to product 2.0. So how do I do that? I come back to my definition, I turn this into 0, and I put 100 here, and I pretty much do the same with my customer canary. 0% traffic to v1, 100% traffic to v2. And I got to just do deploy canary for v1.5, and deploy canary for V2. And now you don't even see the versions getting oscillated. Very soon they'll stabilize, and it will be 1.5 for customer and 2.0 for product. They are in production, they are stable, and we don't need to touch them again. Now I can safely go ahead and delete V1 after the connections are drained and after it is gracefully decoupled from the production deployment. This is phenomenal. This is the power of service mesh, where you can actually turn the knob and fuel your flight while being on the flight. So this is a phenomenal way of upgrading your microservices without touching the production deployment. So, well, if you like this, we can come back and let's say there is a problem with our product version V2. So what we'll actually do is, now this is not product, so this is customer. So what we'll do is we'll update the product to go back to V1. So I'm actually doing a rollback where I'm sending 0% of traffic to V2, but 100% of traffic to V1. And I'm going to repeat the deploy canary for V2. And very soon, 2.0 will be rolled back to 1.0 with no effort at all. And it just, there we go. There we go. So now we have undone what we have did in the previous step. Now product is back to 1.0. So that is the beauty of service mesh and particularly app mesh. I really like the way Amazon has architected this. It's very simple. Currently in its preview, it's currently in public preview, so it only supports CLI with some limited functionality, but that in itself is pretty powerful. Eventually, we'll see a lot of features that are coming to app mesh. So I'm going to do another session on app mesh where I'll focus more on the observability, on how we can actually tap into the telemetry capabilities of this. But this is very powerful, and I'm so glad that the whole demo worked, and the concept is so powerful, and it is going to accelerate the adoption of microservices. All right, and again, all of you can go through the same demo. Watch out for the tutorial at the new stack, and go ahead and clone my GitHub repo and play with the JSON definitions and shell scripts and all of that. It is self-explanatory. So we are almost towards the end of the session, but let me announce a couple of things. So let me first summarize before I talk to you about my next session. So App Mesh is Amazon's own implementation of Service Mesh. Each microservice runs an Envoy proxy coupled with Amazon's own router. There is a control plane that is invisible to you, but handles all the traffic policies. Your AWS CLI pretty much talks to that control plane. Or you can also use SDK, or eventually you can use AWS console to actually monitor this. And I hope Amazon gives us better UX where you can actually drag and change the JSON policies, drag the sliders and turn some knobs instead of updating JSON definitions. Observability will be available through CloudWatch and third-party services like Datadog. So that brings us to the end. And now I want to launch a quick poll. How relevant was this webinar content? Did I deliver what I promised? Did it meet your expectations? Excellent. I only see 60% of you participating in the poll. I really appreciate if all of you can spend a few seconds giving me the feedback. There we go. Now it's about 80%. Fantastic. Thank you. Looks like you found it very relevant. Now I have one final poll before we move to the next one. How do you rate the overall quality? The quality of content, quality of demos, quality of my presentation, the audio visual experience, everything put together. Brilliant. I'm so glad that all of you liked and found it useful. You're happy with the quality, and I'm committed to bring you cutting edge technologies and demystifying the emerging technologies. Thank you again. So now this was all about the infrastructure where we focused on service mesh. I'm very excited to announce the next webinar on February 7th, which is actually next Thursday. And I'm going to bring you convolutional neural networks powered by NVIDIA digits. So this is going to be like a crash course on building a convolutional neural network and then using a wizard style application built by NVIDIA called digits. we're going to do some pretty interesting use case, all the way from training to hyperparameter tuning to deployment and inference. And this is on the machine intelligence track. So if you like what you attended so far, I encourage you to sign up, go to mi2.live, and you can sign up for the upcoming webinar. And this is exactly a week from now. This is going to be another exciting walkthrough of CNNs, and more specifically on NVIDIA Digit. So I want to take the opportunity to thank our sponsors, Newstack, my media partner, where I'm going to publish all the content and the supporting tutorials and context and background. Foghorn, a Bay Area-based edge computing company. It's a startup that is focused on building a cloud-agnostic multi-cloud edge platform. Portworx, a container-native, cloud-native storage company that is bringing stateful workloads to Kubernetes and Mesosphere. So thank you for attending this, and do keep an eye on mi2.live and sign up for my upcoming webinars. I'm committed to bring you quality content on emerging technologies and evolving technologies. Thanks again. Have a great rest of the week and a great weekend ahead. Thank you.